What's up, guys? Back at it again. Another sweet vid popping off right now. Sweet viddy. Let's go viddy time video. All right. I just biked like 3 miles. I don't even know why. It wasn't even a good bike to do it on. I think I pulled my groin. That's all right. Still at it. Got inside. Immediately sat down. I was like, it's sim science time. So let's do this. All right. So let's talk about the different types of bonds that atoms form. So like I said in class, we're starting to talk about how these electrons interact with each other, how different atoms interact with each other to form compounds, to form these molecules that exist all around us. So we're moving on from just atoms into molecules, multiple atoms bond together. So first one I want to talk about in this is covalent bonds. Okay, covalent bonds. All right, so when you have a covalent bond, you have non-metals, okay? So if we go down to our periodic table, our non-metal section is over here, also includes hydrogen, okay? So things that have similar electronegativities, similar ionization energies, like nitrogen, oxygen, fluorine, things like this when they bond together, or when these things bond with hydrogen. Okay, that's typically what we're talking about when we're talking about covalent bond. Say typically, really just always what we're talking about when we're looking at covalent bonds. Okay, so let's talk a little bit about what a covalent bond is. So, covalent. Co is together, like coexist. All right, together, exist together. Covalent is together, and then valent is like valence. Valence, together, valence. Valence electrons together, sharing valence electrons. That's what a covalent bond is. That's what it means. That's what we're talking about. Sorry, I'm some stuff on. Oh, dude. Don't mind the noise. ASMR. So valence shared together. So let's look at an example of this. Let's look at oxygen. Okay. So let's say we have 2 oxygen atoms near each other. So an oxygen atom, look down here, what are we looking at? We're looking at oxygen. Okay, oxygen. Oxygen has 8 electrons and valence electrons in its highest energy orbital. So oxygen's in the second energy level, so it has 2s2, 2p, 1, 2, 3, 4. So 4 in the p, 2 in the s, 6 valence electrons. So let's represent that. We'll do it in electron green. So these electrons, when they're forming, they're going to want to be as far away from each other as possible because they repel each other. So we have 1, 2, 3, 4, 5, 6. And we'll do the same here, and I won't do it in the same order, but set up the same way. Okay, so both of these have 6 electrons, 6 valence electrons. 8 electrons total, 2 in the first energy level, 6 valence electrons in the second energy level. Now everything wants 8. We talked about the octet rule. So oxygen wants to have an electron configuration like neon. It wants to have 8 valence electrons. Every element on the periodic table wants to have the same electron configuration as the nearest noble gas. They're all envious of the noble gases. If you don't remember where the noble gases are, it's this whole group right here. Helium's the exception. Helium only has 2 valence electrons. The rest of them have 8. Okay? Every atom, every element on here wants to be a noble gas. They're jealous. They want to live that high life like the noble gases. They want to be up there in their castles, having their banquets. Okay, they want to have 8 valence electrons. That's the dream. They want to live the dream. So oxygen's out here and it's like, man, we only got 6 valence electrons. What are we going to do? Well, maybe if we coexist, maybe if we come together in our valences, we could kind of have 8 in a way. So this oxygen is like, yo, want to share? This other oxygen is like, okay, all right, so now let's come together, oxygens. Let's make this happen. So now we're gonna line them up over here. We got oxygen, They're gonna line up their electrons. They're gonna go, okay, let's face these two towards each other. And let's just kind of claim both of these. So now this oxygen over here is like, okay, so I got my 1, 2, 3, 4, 5, 6 electrons. Now I kind of have 7, 8 electrons. I'm happy with that. And this oxygen is like, well, I got 1, 2, 3, 4, and then my 5, 6, and I kind of have 7, 8, and I'm happy with that too. So now they both together kind of have 8 electrons. By sharing their valences, they've come to a point where they basically have 8 electrons. So this will normally be represented like this with 2 lines. It's a double bond. Each of these lines represents 2 electrons. Like we saw here, we have 1 electron here, 1 electron here, 1 electron here, 1 electron here. So each line represents 2 electrons. And then it has the rest of its electrons. So it has 1, 2, 3, 4. So 2, 4, 6, 8. This has 2, 4, 6, 8. So they both kind of have 8 electrons now by sharing their valences. So covalent bonds are when they are sharing their valence electrons. Now another example of where this happens that's all around us every day in the air, it's what we drink. And I'm not talking, well, okay, I'm not gonna make an alcohol joke. Okay, so let's say we got oxygen, then we also have, what color should hydrogen be? Let's just go gray. Then we have 2 hydrogens, okay? So what's going on with their electrons? Well, oxygen's still gonna have 6, so it's gonna have 1, 2, 3, 4, 5, 6. Hydrogen just has 1 each. Now, so oxygen still wants to get 8. Oxygen wants to have 8 because oxygen is right here, like we talked about. It wants to become neon. Now, hydrogen is the exception, one of the exceptions to the octet rule, because in the first energy level, the most electrons that hydrogen wants is 2. R2 is 2, either way. Okay, it wants to become like helium. It just wants 2 electrons and it'll be happy because then it has a full first energy level. Its highest energy level will be full. So hydrogen and oxygen are like, oh, what if we share this and we share this, both of these representing 2. Okay, so then this hydrogen right here is like, okay, well now I have my first electron and then I connected to a second, and this hydrogen is thinking the same thing, and oxygen is like, well, I got the best deal because now I connected to 2 other electrons, and now I have 2, 4, 6, 8 electrons total, and everybody's happy again. So this is water, H2O, and it's normally represented like this. So you have your 2 lines. Again, each line represents 2 electrons. You have 2 electrons here. So we have 2, 4, 6, 8 electrons total here. 8 for oxygen, 2 for each hydrogen, and everybody's happy, and we have water. Okay, so that's what a covalent bond is. It's when atoms of nonmetals share their valence electrons. Okay, that's how we get covalent bonds. Beautiful. All right, now let's talk about ionic bonds. Ionic bonds. Okay, so an ion, what's an ion? An ion's an atom that has a different number of electrons than normal. That's what an ion is. So an ionic bond occurs between 2 elements that want to become ions. So that's typically going to be, and let's just erase this all, and we'll start fresh with ionic bonds. So that's typically going to be between a metal, which are on primarily the left side of the periodic table, going down this staircase that we have drawn out, and then a non-metal is over here. So with these, you have well, we'll talk about that in a second. So let's, I know I've talked about sodium chloride before in class, so let's talk about sodium chloride and the ions that it forms and how they come together. So we'll do do sodium in green here. Okay, and then we'll do chlorine in purple. Okay, so here are my two atoms. So let's look at the electron configurations on these two atoms. So I'll do, let's do the rings in orange, why not? So sodium, what energy level is sodium in? Well, let's label our periodic table. First, second, third, fourth, fifth, sixth, seventh energy levels. Sodium's right here. Sodium's right here in the third energy level. So we know it's gonna have 3 energy levels around it. So let's see how good my circles are. 1, 2, 3 energy levels, okay? And what's that configuration gonna look like? Well, the first energy level is full, so that's 1s1, 1s2. 1s2 is a full first energy level. Second energy level, we have 2s1, 2s2, 2p1, 2, 3, 4, 5, 6. Okay, so 2s2, 2p6, second energy level, 8 electrons total, octet, full second energy level. And then sodium's right here, so it's 3s1. It's gonna have 1 electron in its third energy level. That's its valence electron. Here's the valence electron. That's why sodium is represented in its Lewis dot structure just as Na with 1 dot, because it has 1 valence electron. Okay, so there's that. Now let's look at chlorine. Chlorine, which is over here, I'm doing it in orange, mixing up the color a little bit, that's all right. Chlorine, again, the third energy level, so we need 3 circles. 1, 2, 3. Okay, so again, 1s1, 1s2, full first energy level, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6, 8 electrons in the second energy level. And then chlorine in the third energy level has 3s1, 3s2, 3p1, 2, 3, 4, 5. Okay, so 3s1, 3s2, 3p1, 2, 3, 4, 5. Okay, so the chlorine atom in its outermost energy level, in the third energy level, is going to have 7 valence electrons. Okay, 7. So it has an open space here, and I think you can probably see where I'm going with this. So sodium over here is thinking, if I can just get rid of this 1 electron, get rid of my third energy level completely, then I'm gonna have a full octet in my second energy level. And it's gonna be satisfied because it'll have, it'll achieve an octet of 8 electrons at second energy level. And chlorine's thinking, if I can just get an electron here, then I'm going to have a full third energy level. I'll have an octet in my third energy level, and then it's gonna be happy. So what do you think is gonna happen? Well, sodium is gonna throw out its 1 electron and is gonna give it to chlorine. Okay, so let's draw out those Lewis dot structures again. So we have sodium here with 1, and then purple, chlorine with 1, 2, 3, 4, 5, 6, 7. So this electron is going to go right here. So sodium's losing an electron and chlorine's gaining an electron. So when sodium loses that electron, it's losing 1 negative subatomic particle, so it's going to become positive. It has 1 more proton now than electron, and it's a positive ion. Chlorine's gaining 1 electron, gaining 1 negative subatomic particle. Now it's going to be negative. It's a negative ion. So positive ion is a cation and negative ion is an anion. And together, these two charges, the positive and negative, attract them to each other. So that's what holds these together. You have your final product is NaCl, sodium chloride, which is table salt. We eat it all the time, even though these elements alone would kill us. When it bonds together, it's happy, they're satisfied, they're not reactive, and we eat it all the time to season our food. We have salt. okay? So with ionic bonds, like I said with covalent bonds, with ionic bonds, chlorine's out here, and it's saying, why don't we share? Why don't we share? And sodium is just saying, I don't even want to share. I don't even want to share. Okay, so it's an ion. It's saying it doesn't want to share its electrons. It's going to give it to it. Just take it. Why do I have a bowl and then quotes? I don't know. But sodium's just giving it away. It's saying just take it. So it gives it away to chlorine. So these are not sharing electrons. Like this arrow I drew is just giving it away. What's keeping it connected is this positive and negative charge that draw them together. Okay, and then they form a compound based on that electrostatic energy between them. And when you have a positive charge and a negative charge, it balances out. And therefore this end product, which I can't circle and square enough, this has no charge on it because the charges balance each other out. So that's how you get sodium chloride. That's an ionic bond. Sodium chloride is a very common example, but really anything other than hydrogen. Hydrogen is not included in the alkali metals, but all of these alkali metals, they really want to react with stuff. They really want to lose one electron and get to the configuration of the nearest noble gas. So they're ready to react, especially with the halogens over here that have 7 valence electrons and really want a valence electron. So if you remember back to our periodic trends, switch colors so you can see, sodium has a very low ionization energy. It's really easy to take that electron away from sodium, okay, compared to chlorine down here at the other end. Chlorine has a high electronegativity, a high ionization energy. It's hard to take an electron away from sodium or from chlorine. And chlorine has a high electronegativity. It really wants to attract a new electron. Sodium doesn't have that. But sodium's low ionization energy, so let me write this out. Sodium, low ionization energy, and this is compared to chlorine, chlorine, and then chlorine's high electronegativity. I'm running out of room. Electronegativity cause this. So ionization energy is how difficult it is to take away an electron. It's low for sodium. It's easy for this electron to go over here. Chlorine has a high electronegativity. Electronegativity is the ability of an atom to attract an electron. So chlorine is pulling this electron toward itself. Okay, so those trends come in handy here when you look at this. So this video is getting a little long. I'll probably do another one on metallic bonding, or we'll touch on that really quickly in class. It's pretty simple. But quick review, covalent bonds, covalent, covalence, sharing valence electrons between two atoms, between two non-metals. Okay, and then ionic bonds, ions, okay, 2 different ions with charges. When electrons change, you get an ion with a charge, positive cations, negative anions. These 2 ions and the forces of the charges draw these 2 together when one gives electrons to the other, and they come together to form a compound that's neutral. They balance each other out, they form a compound. Okay, so those are the basics behind what these 2 different types of bondings are and why they're different.